lecture is going to be short because we already have covered registers and counters so far, as you know. We actually looked into synchronous and asynchronous counters, and one of the asynchronous counters example was the ripple counter, right? That the T flip-flops are connected to each other, and there is only one flip-flop that is connected to clock signal, and the rest of the two flip-flops are connected to the outputs of the previous T flip-flop, right? So there is a cascade of these T flip-flops. They are triggered in different times, but that's good because that creates the countering functionality. So there were two things that I failed to cover because of the time. Last time in our last meeting was one of them was the ring counter, the other was Johnson counter, and I'm going to start talking about them today. If you don't have questions about the previous stuff that we covered. Okay, so let me first introduce the motivation for you. Why are we learning about ring counters and Johnson counter? Okay, these are slides, by the way, from our blackboard. So first of all, we will, as any one of you might guess, that any digital circuit needs, timing information, timing signal, okay? Without time, we wouldn't know where we are. And digital circuits are the same. You look at the time, before 1 p.m., you aim to be in the class because digital circuit system class will start at 1 p.m. That's why you arrange yourself, all your schedule according to that timing. And same principle applies to hardware. Hardware also cares about timing, and in order to generate that timing, we use counters most of the time. However, when you count things like it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, that doesn't really mean anything about the hardware. Hardware needs to be turned on or off, okay? So if you got modules, for example, let's say it's module 1, and module 2, and module 3, and module 4. So there are 4 modules. These are hardware modules, and every one of them, of course, has an enable signal. So enable input, not a signal, enable input. Okay? These are all enables. And what I want to do is I want to first enable module 1, and then module 2, and then module 3, and then module 4, and then back to module 1, and then module 2, module 3, module 4, and then back to module 1, and so on and so forth. Okay? So that means I have to generate a 1 here, a signal saying that it's a high logic value, a 0 before here, 0 here, 0 here, at a specific time instant, which I'm going to call a period. Okay? So in one period of the clock, so that is my period, right? Period. At this specific period, I'm going to say, okay, module 1, why don't you just turn on? Okay? And then do whatever you're supposed to do, process information, and then you close in the next period. In the next period, that's the second period. In the next period, module 2 now turned on. This is turned off, and off. That means in the second period, I'm going to send 0 for module 1, 1 for module 2, and 0 for module 3, and 0 for module 4. That's the next period. Okay, that's the first period, second period. Okay? And you will use that kind of architecture in your CPU design. Because in your CPU design, there are many hardware blocks. Some of the blocks has to be enabled, some of them have to be disabled. Otherwise, those hardware that needs to be disabled will operate on the data and corrupt the data. Okay? So, in the next period, as you can guess, you will disable this one, enable this one, and disable this one. And finally, you disable this one, disable module 2, module 3, and enable module 4. Okay? That basically is just like counting, right? Module 1, 2, 3, 4, and then back to 1, 2, 3, 4. Okay? So if you continue that, you actually completed the period, by the way, right? The period of this sequence is 4. Because as you can see, this is the first output of that circuit, and then, the counter. This is called ring counter, by the way. It's not like this, right? The conventional counter starts from 0, 0, 2 bits to count 4, right? I mean to count modular 4. It starts from 0, 0, goes 0, 1, and then 1, 0, and 1, 1. That corresponds to 0, 1, 2, in decimal format, 3, right? And then it goes back to 0 again. So this is your conventional counter. Like synchronous counters we've seen, the asynchronous counter we've seen with T flip-flops, that does exactly that. Those counters are always counting using minimum number of bits to count those decimal numbers. However, this counter is a bit different because it uses more bits and more flip-flops, of course, to count 4. This is 1, this is 2, this is 3, this is 4. It's just like mapping these output sequences with the decimal value. So in this counter, we basically map 1, 0, 0, 0 to 0, in decimal format, and 0, 1, 0, 0, 2, 1, 0, 0, 1, 0, 2, 2, and 0, 0, 0, 1, 2, 3. Okay, so I use now 4 bits to map to these decimal values. Okay, why? Well, because this is just convenient for me. Because these ones can be used to enable different modules in my hardware. Okay, I cannot use this counter for this specific purpose because it's not generating those ones in the way that I described these enable signals. All right? But, of course, there is a simple transformation going from to here, right? What should I use here? A combinational circuit that will translate this output to this output. Can you tell me which combinational circuit you learned can be used to translate this 2 bits to those 4 bits?
Decoder?
Is this decoder? What's that? Encoder. That's encoder. Actually, I mean, going from here to here is encoder. Sorry about that. This is decoder, of course, because this is encoded values, right? So decoder generates, remember, decoder generates minterms. So these are actually look like the minterm. This is the first minterm, second minterm, third minterm, and fourth minterm. So therefore, if you have a counter, so let me draw maybe here with a different color. I want to erase the rest of the circuit. So maybe if you have a conventional counter here, okay, that generates 2 bits. Remember that conventional counter that counts forward does not need any input. You don't need to provide any input for that counter. It just counts. And it generates those bits, 2 bits. 0, 0, 0, 1, 1, 0, 1, 1, and then goes back to 0, 0, 0, 1, 0, 1, 0, and 1, 1. At every clock tick, every clock cycle, okay? So now you connect that to a decoder, because if you have got 2 inputs, you got 4 outputs in the decoder. So this is 2x4 decoder, right? It decodes that 2 bits to minterms. And we know that if this is a decoder, only one of the outputs could be 1, the rest of them should be 0, right? Because these are minterms. And that's exactly the description of the output of a ring counter, okay? So therefore, this is, as you count here, generate those binary bits, 0s and 1s, 2 bits. This would generate actually 1 that is circulating, okay? That's gonna be circulating. If you put, for example, a lamp to each one of these outputs, a LED, for example, so that LED would actually go back and forth, it's like in a circle, okay? It's going to lit, for example, this one is going to lit in the first clock cycle, and then this is going to lit, this is going to turn off now, and then this is going to be lit, and then this is going to be lit, and then go back to the first one again, okay? So it's going to actually circle around, and then those LEDs will be, light on. Okay, so these 2 is considered to be the ring counter. Okay? And ring counter uses 4 bits, right? So there are 4 possibilities here out of 4 bits. You know that in 4 bits, if you've got 4 bits, you can count up to 15, right? It starts from 0 to 15. But this, counter does not exploit that fact. It just uses only the 4 out of 16 possibilities to generate a counter that can count from 0 to 3, okay? But it's convenient for hardware because it can be used to enable different modules of the hardware, okay? Okay, so this is good. However, there are a couple of problems with this ring counter, okay? First of all, you can also draw, by the way, the finite state machine representation of this counter as being 4 states, right? And each state is represented by those 4 bits, 1000, 0100, 0010, and 0001. And that is your finite state machine representation or state diagram of this counter. Okay? We just used, instead of 2 bits, we just used 4 bits to represent those states. Okay, so there are 2 problems with this counter, actually. First one is that it starts from 1000. If it starts, so let me draw the circuit diagram for this round. It's pretty simple, by the way. You just use 4 flip-flops, as you can guess. Okay, so let me just erase this bits and then draw the circuit diagram that generates these sequences. Since it's pretty easy, we're going to just use D flip-flops. I can replace always D flip-flops with other types of flip-flops. So you got D flip-flop, 4 of them, stacked together. This is my D, Q, D, Q, D, Q, D, Q. And of course, there's a clock signal. It's a synchronous circuit, so they're all connected to the same clock, right? And now what I do is, to be able to create a ring counter using 4 flip-flops, I have to take this Q and then feed back to D, right? And of course, I have to initialize this flip-flops with 1000, right? So in the initial, like in the beginning of the circuit, this has to store a 1, this has to store a 0, 0, and a 0. If you start clock signals, if the clock signal pulse starts ticking, then this 0 is going to be pushed back to here, right? And this 1 will be pushed back to the next flip-flop, then this 0 will be pushed back to the next flip-flop, and then this 0 will be pushed back to the last flip-flop, and it will generate the next sequence, valid sequence, which is 0, 1, 0, 0. In the next clock cycle, because this is a shift register, right? It just shifts back to onto itself. In the next clock cycle, this 0 will be now pushed back here, and this entire sequence, 0, 1, and 0, will be shifted to the next 3 flip-flops, right? And these are these next 3 flip-flops. That means there's 0, 0, 1, 0. And finally, after 1 clock cycle, now this 0 is pushed back to the beginning, and then you get 0, 0, 0, and 1. That is the last sequence you can obtain at the output of this flip-flop. I'm talking about the output being, this is the first output, let's say S0, this is S1. Well, by the way, these are all connected to each other, right? Otherwise, it will not shift. Sorry about that, I forgot that. So this is S2, and I have got S3 here. Okay? S0, S1, S2, and S3. So these are the bits that I'm talking about here. Okay? So, there are, as I said before, 2 problems. One of them is that you have to initialize it. Okay? You have to put 1 in the beginning, flip-flop, and the rest of the flip-flop should assume zeros. All of them. Okay? The other problem is that it can only count up to 4. Question? No, go ahead. Yeah. I assume that I stored that 1 in the beginning of the operation. Yeah, that's a big problem, by the way. Yeah, I just assumed that I stored 1 by an external mechanism. Okay, I just connected, for example, a multimeter, for instance, and then make sure that this stores 1 before I start its operation. Because in the beginning initialization, if I initialize this circuit with 1, 0, 0, 0, and then start operating it by turning on the clock, then it will not be a problem because that 1 will circulate anyway, and it will not change, of course, throughout its operation. So therefore, initialization is an issue for this ring counter. That's the first challenge or problem, let's say. The second problem with this circuit is that it can only count up to 4, like 0, 1, 2, 3, the mode 4 counter. However, it uses 4 bits. So with 4 bits, you can actually count from 0 to 15, like 16 different possibilities. But this can only count up to 3, 0, 1, 2, 3, right? So people actually question it. People just, the attractive part of this circuit is that this does not use any gates, right? It's just flip-flops. Pretty simple design. That's the most attractive feature of this circuit. That's why people prefer this circuit. However, the problem is that it does not count very well because it's not using its potential. And the other thing is that you have to initialize it. Okay? So, people now devise different approaches to this problem while they keep the complexity in mind, because without any gates, your complexity is reduced. There's no combinational circuit here. It's all sequential circuit elements, right? The flip-flops. So people thought about that. They gave a lot of thought into this, and they finally came up with the Johnson counter. Okay, as the name implies, is the inventor's name is given to that counter type. So let me just briefly talk about that counter as well. It's an extension to this counter, by the way, so I'm not going to erase this. Instead, I'm going to use the other side of the board to draw the Johnson counter. It's pretty much the same, actually, but he actually proposed a solution with minimum number of gates to solve these two problems of the ring counter. Okay, count more. Okay, just don't stop at 3. Maybe you can count more because you got the potential. The second problem is the initialization. So, the Johnson counter is as follows. We have, again, since I've started with 4 flip-flops, I'm going to go with the 4 flip-flops, but it's general. You can use any number of flip-flops and apply the same idea. So there are 4 flip-flops, D flip-flops again. Okay, excuse my drawings. I'm not really good at drawings at this point. So these are cues. Okay, and these are clock, signal. Sometimes I forgot, I look at my previous videos, I noticed that I sometimes forgot to draw the clock signal. Okay, so excuse my writing, sometimes I do that. But clock signal has to be out there. It's like a heartbeat, so you can't forget them. Okay, so for this particular, so these are Q's, of course, and you remember that these were Q primes, right? Okay, so one of the things that Johnson did, he connected these Q's, okay, to of course preserve the shifting property. It still has to shift, okay? As long as you have a clock, it will shift everything in those stored on those flip-flops to the right, okay? So he preserved that. But one of the things he did is instead of using the output of the last flip-flop from the Q output, he uses Q prime, okay? And then fed back into D, okay? That's the first, let's say, workaround to be able to, refrain himself from starting from this weird initialization, 1, 0, 0, 0. So instead of using 1, 0, 0, 0, now you can use 0, 0, 0, 0, which is the default initialization given to the flip-flops. In other words, now you can start without doing any initialization because those flip-flops are usually, by default, initialized to 0. Okay? They've got their own, small circuit that establishes those initializations. So therefore, you start from 0, 0, 0, 0. Okay? Now, would that be all right? Well, we shall see. It will be all right. Why? Because this will generate 0, 0, 0, but you're not really feeding that 0 back to the inputs of the first flip-flop. You're basically feeding back to Q prime, which is not a 0, it's a 1. Okay, so that means this 1 in the next clock cycle will be shifted back onto this flip-flop, making this 1, and the rest of the all zeros will be shifted to the right. Okay, these zeros now will be shifted to the right. All right? Everybody are sync with me? You guys have been able to follow? You got a question?
Won't it spam 1 until it reaches the end of the flip-flop?
Say again?
In the next cycle, I presume it's going to be 1, 1, 0, 0.
Oh, yes, yes. So you're thinking about the next clock cycle. This is still 0, right? So yes. That's going to be now 1 fed back into the, this first flip-flop. So it's going to make it 1, 1, 0, 0, right? Because that one is going to be shifted to the right, this is going to be shifted to the right, and this is going to be shifted to the right. Correct. Your question is?
I mean,
this is not, that doesn't really seem like we're generating something similar to that. Absolutely, I'm going to come to that. Okay, I'm going to come to that. Okay, now I got 1, 1, 0, 0. Okay, is everybody happy with that? Questions? We good? Okay. So now we got 0 here, which is going to make it 1 again, and then 1 is going to be pushed into that circuit. So you're going to have 1, and those 1, 1, 0 is going to be shifted to the right. You got 1, 1, 0. Okay? And in the next clock cycle, we got this 0 now becomes 1, and then you push that 1 into from the beginning. You got 1, 1, 1, and 1. We're not there yet because you have to keep doing this until you hit 0, 0, 0, 0 again. That is going to create your period actually, because these sequence generators, these are sequence generators by the way. It generates sequences, and you have to figure out the period of the sequence generator. Okay, the period is not there yet because we're still generating absolutely different sequences. Okay, for example, for the ring counter, I started generating at 1, 0, 0, 0, and then I go to this one, and then go to this one, and then go this, and then I stop. Why? Because the next sequence is going to be identical to the first one. That's why. And period of that sequence generated is 4 because it generated 4 sequences. Okay? So now I'm doing the same thing. I'm applying exactly the same idea to Johnson counter. Now I'm actually applying, actually ticking the clock and to see those sequences that are generated until I hit the one that was the initialization. Okay, that was the initialization sequence. So let me continue now. Let me move on. So this now becomes 1. So when you have a 1 at the last flip-flop, the output Q prime would be 0 now. So now 0 is going to be pushed into the shift register. So you got 0, 1, 1, and 1. Still, this is something that I haven't seen before. Okay, so I still keep ticking. So now this 1 becomes 0. So I got 0, 0, 1, 1. Not there yet. So I continue. I took 1 and then make it 0. You got 0, 0, 0, 1. Okay, not there yet because I haven't seen this sequence in my previous sequences. So I still do that. So this is 1, becomes 0. So this is 0, 0, 0, 0. Bang, because now this is the first sequence. So that means I actually have to stop here. Would actually give me how many different sequences? 8 sequences, right? All right. I've got 8 different sequences. But those sequences do not look like the format that I have here. The format that I described earlier was in each bit position, there is only one 1, logical 1. The rest of them are 0. That's the format that I defined because in that particular way, I can enable modules 1 at a time. In order to come to that format, in order to resemble this output, make the output resemble to the format that I just described, because that's going to be useful for hardware perspective, then I have to apply some gates here, unfortunately. Okay? That's the pitfall of having 8 sequences. Okay? Without any gates, there's a limit. That's 4. You can't go beyond 4. And that's the ring counter. That's what the ring counter gives you. If you would like to expand the number of possibilities at the output to 8, then you have to use some kind of transformation to generate this sequence to generate, since there are 8 of them, right? So these are 8 sequences. So in order to generate the format that I just described, then I have to have 8 bits, right? Because the format here implies that there are 4 bits, that means there are 4 sequences. Okay, perfect, bingo. I have 8 sequences, then I have to have 8 bits. And only 1 at a time, one of them can be logical 1, the rest of them are zeros. Okay, so therefore, for example, I would just do some kind of transformation, meaning that it's a combinational circuit, some gates. It's going to generate 1, 0, 0, 0, 0, 0, 0, 0. 8 bits. Now in the next, when this shift register assumes this state, 1, 0, 0, 0, or that sequence is just pushed out, then it will be 0, 1, 0, 0, 0, 0, 0, 0. And blah, blah, blah, blah, blah, until we hit the last one, 0, 0, 0, 0, and 0, 0, 0, 1. Now this is the format I like, because this is the format just like the ring counter output. Now I can enable 8 different modules instead of 4, okay? How about this transformation? Well, it's pretty, not very hard to do because now each one of the columns here, let me use another color for you. Each one of these columns here are actually functions of the inputs. Okay? For example, this column here is 1 here, and the rest of them are zeros. And those are the inputs, A, B, C, D. And you know how to go from 4 inputs to one specific function, right? Using Karnaugh maps, and you learned about that. Okay? But instead of going through that hurdle, because you've got 8 different functions, so you have to apply the Karnaugh maps to 8 different outputs. Okay, that's going to create 8 different, I mean, you can, if you've got time, please go and verify it. But if you look at this inputs, one of the things that I realized, I just took A and D for example. A and D, for this particular, just look at these columns, this one and that one. There's only one place where both of them are zeros. You see, this is the place where they are both zeros. The rest of the locations, this is 1, 0, 1, 0, 1, 0, 1, 1, 0, 1, 0, 1, 0, 1. That's it. Right? This is the copy of the first. So you can see that. There's only one place where A is 0 and D is 0. So therefore, I'm going to just say F is equal to A prime D prime. Because that's the only place where A and D are both zeros, it's going to give you 1. The rest of them are zeros. Okay? And you can do the same thing for this function, that one, and that one, this one, this one, this one, and that one, in a similar way. Okay? For example, let me just give you the second one as well. For example, look at A and B. A and B are, A is 1 and B is 0 in only one place, and that is this place. 1, 0. The rest of them are 0, 0, 1, 1, 1, 1, 1, 1, 0, 1, 0, 0, 0, 0. There's only one place that they are 1, 0. So that means I can just use A and B prime. That's going to give me what I want. That is the second column up here. Okay, that's what I want. So this, for example, second column would be, let me just not use function anymore. This is going to correspond to A, B prime, for example. Okay? Now, using the similar idea or using Karnaugh maps in any number of methodologies, any type of methodology you use, you come up with these functions. Okay? Why are we learning about these functions? Because now, what that means is that, for example, in order to generate this 1, you connect a NOT gate to A. This is my A, by the way. So that's my NOT gate. And B, another NOT gate, which is this one. And then AND them together. Okay, to generate your first, this is F0, it's going to create F0. And similarly, for this one, let me just call it F1. That is A and B prime. So this is my A. Oh, by the way, you don't even need to use NOT gates, right? Because A NOT is already there here, so you don't need to really spend the NOT gate here because this is actually now available. And similarly here too, you don't need to do that. Just connected this to this wire because this is already Q prime. Oops. Yes. Okay? That's only single AND gate. Okay? And for the second function, A, B prime, you got A already, and B prime is right here. You AND them to generate F1. Okay? So now you can go through and do this functionality. So therefore, there's going to be a single AND gate to generate F0, and then single AND gate for generate F1, and blah, blah, blah, blah, blah, and then another gate to generate F7. Okay, now we talked about this transformation. Now I can generate a format, a counting format, that is identical to the format that the ring counter generates. Okay? So so you see, the Johnson counter solves two problems, I mean, almost perfectly, let's say, but not perfectly, of course, because now you're using combinational circuits. But almost perfectly. The first one was the initialization problem. So now you can initialize from 0, 0, 0, 0. Which is good, okay? You may not have the, sufficient equipment to initialize the ring counter to 1, 0, 0, 0, okay? So this is good. The second one was expanding the number of possibilities. The previous 3 now, but now we're able to count from 0 to 7 in a format, it's just like the ring counter output. Okay? But of course, the price we pay is the combinational circuits. In other words, we use 8 different AND gates here. Okay? 8 AND gates to be able to generate a format that is similar to or identical to ring counter outputs. Okay? That is the price we pay. However, now you can enable 8 different modules by sending enable signal to each one of them at a time at each clock cycle. Okay? Question about the Johnson counter? You got a question?
So I'm assuming 8 AND gates is cheaper than adding another 4 D filters.
Of course, yes. Yes. That's the assumption. Right. Any more questions about, go ahead.
Could you show again how can we require F0 and F1?
But you couldn't get, well, how A prime and D prime results?
Yes.
Okay, so my suggestion to you, in order to convince yourself, just treat this column as an output of the function, and this is your inputs, okay? Go ahead and draw a truth table. You can figure out that the Bloom function that corresponds to that kernel map is going to be as small as this one, A prime, D prime. The way that I described is easier because I looked at these inputs and I figured that, when I look at these inputs, and there are don't cares by the way, right? Because there are 8 of the possibilities out of 16 is already drawn on the table, on the board, but the rest of the other 8 are just don't cares. That's why we actually have a minimized Boolean expression because of those don't cares. Okay? Anyway, I just look at these inputs and I figured that when I look at the column A and column D, there's only one place in this table where A is 0 and D is 0. You see? That's the only place I have got A 0 and D 0. The rest of them are 1 0, 1 0, 1 0, 1 1, 0 1, 0 1, and 0 1. So therefore, if I let F0 to be A prime D prime, that's going to give me 1 in only one place, and that is the first row. The rest of them should be 0. Okay? If you don't believe me, you can try. For example, you can just give A to 1 and D to 0. That's going to give you a 0, right? It's because it's A prime D prime. Okay? Because A prime is 0, since A is 1. So every other possibility in this columns is going to give you 0, 0, 0, 0. Only one of them, the first row, is going to give you 1, and that's exactly what I'm looking for. That's why I asserted that F0 should be A prime and D prime. Is that clear? Okay. Any more questions? Go ahead.
Can you solve the third row too?
Third row?
Yeah.
You mean
That one.
you mean F2? Yes, F2. So let's just look at the F2.
BC prime. BC prime.
BC prime. Okay, so your friend. So let's check. Just check. Checking is easier, right? So let's just check. So there's a B and C prime. So if you look at the BC prime, this is going to give you 0. This is going to give you 0. This is going to give you 1. Okay. 0, 0, because C prime is 0, right? 0, 0, and then B, C prime, B is 0 now. It's 0. B is 0, B is 0. I'm sorry. You don't need to consider that. So that means all of them are 0. Only in this particular row you're going to get 1, and that's exactly what you're looking for, right?
And third one is also CD prime, right?
It's on the slides. So you can figure out, I've actually written down the Boolean expression that corresponds to each one of them. But believe me that each one of them can be implemented using a single AND gate.
And we are considering A, B, C, and D as an input.
These are the inputs to this combinational circuit.
Yeah.
But these are the outputs of this shift register or counter, let's say. Okay? This counter creates actually A and A prime, B, B prime, C, C prime, and D, D prime, right? So you've got all A, B, C, D, and A prime, B prime, C prime, D prime. Okay, and those F0, F1, and F2 are functions of A or A prime, B, B prime, C, C prime, C, D, D prime. So you don't need any other gates other than AND gates. Okay, that's why I use only 8 AND gates here to generate F0 to F7. Okay? You seem to be confused. Do you have any questions? No? Yeah. Then I'm confused. Any questions? No? Okay. Well, of course, our discussion is not finished because you may be asking, that was the question I was expecting you to ask, is that, well, this is good. We got this ring counter that can count 4, okay, in this format. This Johnson counter is able to count up to 7s from 0 to 7 in the same format. But we've got 16 possibilities. Why don't we just come up with a counter that can count from 0 to 15 in the same format? Right? That's the most other extreme. Right? The ring counter is on one extreme. You don't use any combinational circuits to generate a counter that is in this format. How about the Johnson is just like in the middle because it generates 8 states, 8 sequences. But maybe on the other extreme, you can have a counter that can generate all possibilities. In other words, it starts from 0, 0, 0, 0 up until 1, 1, 1, 1, 1. But all possible binary combinations. Would that be a counter? I mean, do we have such a counter? Right? That might be another interesting question. Okay? That leads to a discussion of something called maximum length sequence generators. Okay? And that is used commonly in communication technologies. Okay? People in the hardware, these are actually mixed signal processors and mixed signal engineers. Those actually use those maximum length binary sequence generators to be able to count, for example, to maximum possible. Okay, and those actually use in different technologies, such as you may have heard of maybe time division multiple access. Did you hear about such things before? Okay, so this is code division multiple access. You know, in multiple access communication scenarios, people actually have to be given a code, and those codes are generated using those maximum length sequence generators. Okay, that's another interesting application of such sequence generators. You've got a question before I proceed?
Is it about the cost, price?
Yeah, cost complexity trade-off actually. Right. This is very cheap actually, but it only creates 4 states. This is a bit complex because now instead of on top of this 4 flip-flops, this connection is not going to cause you a lot of cost, of course. It's intelligent. It's very clever, by the way, clever modification or tweak to this circuit. But you have to have extra combinational circuits here, which adds to the cost of the system. However, if you go to maximum line sequence generator, which I'll show you in a bit, it's going to create, more cost, but it will give you more states. Now you can count up to 15, for instance. Okay? So let me erase this part of the board since you guys are. Do you want me to use that word, this one? Are you guys okay with this? Or maybe I can use this. Would that be all right? Okay, so let me erase this and then draw my last circuit here. This is not in the slides, by the way, okay? It's just an additional stuff I wanted to cover since we got some time, okay? Because you may be, wondering about what's the next step from the Johnson counter, right? Johnson counter is a good expansion, it's a good extension to the ring counter. It helps us get more states, but that's not the maximum number of states. So I'm going to give you another example, okay? This is my flip-flop. Again, 4 flip-flops. I carry on my examples with 4 flip-flops still. So now instead of having this, I'm going to now, these are Q, Q prime, Q, Q prime, Q, Q prime, Q, Q prime. These are D inputs, and these are actually connected. D, D, D, D. Okay, now next thing I'm going to do is take this Q prime now, okay, and then take this one as well, XOR them, and then push that back into the D. Okay, so instead of just adding this, carrying this or moving this bit to the beginning flip-flop, this first flip-flop, why don't we just XOR it with the current value of this flip-flop and then push it in to this flip-flop, okay, rather than just moving it. This is an extra XOR, okay? So you can actually replace this with an XOR gate. A simple modification. All right? Let me see if I can draw it well. Okay. Okay? One XOR gate. All right, let's see what happens. Question? Forgot what clock? Yes. Sorry. So it's clock signal, and then clock signal. All right, now I'm going to start with 0, 0, 0 again, of course. All right. Now the next one would be, this is gonna be 1 because it's Q prime, and this is my 0, right? So now I XOR them, which creates 1. So the new value of this is going to be 1. I mean the first flip-flop state. The rest of them are just shift. A good thing about that is just you don't need to worry about the rest. It's just a shift value. So I'm going to just write 1, 0, 0, 0. Okay? Now in the next clock cycle, this is going to be 1. This is going to be 1. XOR them. 0. You got a 0. The rest are just going to shift to the right. Oops. Now you got 0, 0. Now this is going to be 1. This is 0. XOR them. You got 1. 0, 1, 0. Alright? Now this is going to be 1. This is 1. XOR them. 0. New value will be 0. The rest of them are going to be just shifted. I continue doing this because I haven't hit in one of the previous sequences yet. Okay? Now this is 1. Becomes 0 because I took the output from Q prime, remember? That's 0 and that's 0 XORed to generate the next state of the first flip-flop, which is 0. 0, 1, 0. And then this becomes 1. This is 0. XOR them. 1. You got 1, 0, 0, 1. This becomes 0. This is 1. XOR them. You got 1 and then 1, 0, 0. This is 1 now. 1, XOR them. You got 0, 1, 1, 0. I haven't really come across any one of these sequences yet, right? Are you checking it? Okay, so that means I have to continue, unfortunately. So this is 0 now, becomes 1. This is 0, XOR them. You got 1, 0, 1, 1. Now this is 0. This is 1, XOR them. You got 1, 1, 0, 1. And I've got now this one 0. This is 1. That gives you 1, 1, 1, 0. Okay? How many of them now? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. This is now 1. This is 1. XOR them. That's 0, 1, 1, 1. Have I seen this before? Probably not. So this is 13. This is now 0. This is 0. XOR them. You got 0, 0, 1, 1. Have I seen this before? No. No. Okay. This is 14. Hopefully this is the last one. This one becomes 0. This is 0. XOR them. 0, 0, 0, 1. Have I seen this before? No. 15. Okay, let's just continue. This becomes 0. This is 0. XOR them. 0, 0, 0, 0. That's the first one. Okay? Now we go back. Did you understand why I'm calling this maximum length sequence generator? Because it generated all the possible binary sequences that you can make using 4 bits. Okay? That's why people call it. This is not the only design, by the way. I'm going to talk about it in a minute. This is not unique. Okay? It's called maximum maximum length, right? Length sequence generator. Okay? Or bit sequence, right? Maybe that would be much more better name. This. I know that it's tedious work because you have to go through all of them. And since you got 4 flip-flops, that creates 16 possibilities, and we wrote them down, jotted down on the board right now. All right. Now, of course, you have to generate the format that we are familiar with, right? So that means this is going to go to 1 and 15 number of zeros. And then this is going to have to go to, let's say, 0, 1, right, and 0. So we got 14 zeros here, etc., etc. So that means you have to have a translator here. Translation circuit. Not very hard. Again, you know, there is no don't care here, so probably you have more combinational logic here, right? Yeah, so unfortunately, if this were in order, meaning that this one, the second one, third one, and the fourth one is not this one, but maybe 1100 maybe. 1100. Where is it? Oh, so here, for example. Okay, so this, if this was a classic counter, 4-bit counter, then you could just put a decoder here, right? That would generate your, the same format you have with the ring counter. But that's not in order. You can see that it's not in order, so it's not going to generate the way you like it. However, of course, you can still use a decoder, but now you have to map the outputs of the decoder to the appropriate locations. You know what I mean? So let me just give you a hint about how to do this. For example, let's just put this input to a decoder. So you got 4 inputs, right? And 16 outputs. Okay? So when you have 0, 0, 0, 0, that would actually create a 1 here and zeros here, right? All of them are 0. That's exactly what I want from my format. So the first output of the decoder goes to the first output of the circuit. So that's my circuit, let's say. So because I'm designing a counter, right? So the counter's first output is actually connected to decoder's, let's say D0. That's my first output of the decoder, D0. Okay? And for this one, for example, you got 1, 0, 0, 0. Okay, I actually know it's going to create this to be 1, the rest of them are 0, okay? If I connect them, of course, in reverse direction. But still, I know that this is going to create me one of those decoder outputs, actually the second decoder output to be 1, the rest of them are 0, okay? So therefore, I'm going to connect that to the circuit output, D1. Okay, now this is going to be your next decoder output, so no problem with that. I'm assuming this to be LSP, by the way. This is to be MSP. If that causes some of you guys to, wonder about what's happening. This is my LSP, this is my MSP. Okay, this is not conventional. I know I started in MSP from the left-hand side, but this is kind of, that's why I said I reversed the direction of MSP and LSP. So this is now 2, right? The decimal 2 now. Okay, and that is the third output of the decoder. So that means I'm going to just connect D2 to the output. Now it's going to change now, right? Because this is not 3. Okay, this is LSP, this is MSP. This is not 3, decimal 3. Decimal 3 is actually given in here, right? This is the 8th output of the decoder. Okay, that's why I'm going to just say this is D7 connected to the 4th output of the circuit. Okay. Now you can map them, in different way this way, and you still have a format that is quite similar to the ring counter. Okay. You just need that mapping. The reason that I introduced decoder here, I actually saved you from drawing corner maps, 16 different corner maps, and optimizing and etc. Right? Because decoder already generates those type of outputs. All you have to do is just to do the mapping. Okay, to the circuit output. Decoder output turns out to be not equal to the circuit output. Okay, but all you have to do is just do some kind of mapping without any gates, right? Yes. So without any gates. All right, good. So let me come back to my uniqueness of this circuit. Okay, so the way that people usually introduce these circuits is with an input. In other words, there's an XOR here, Let me just throw an XOR, extra XOR. Okay, and this is your input. Okay? That's why people usually express this in a polynomial form, where you have an x to indicate the delay. Okay? So for example, here, input is not delayed, but those flip-flops causes a delay. So for example, input is actually going into this flip-flop with an additional delay that comes in, right? So therefore, there is a delayed version of input, okay? Input itself, and 4 delayed version of the input, right? So that's why people call this as a polynomial, being x to the 4 plus x plus 1. To be the polynomial that represents this shift register with all these XORs and etc. This x4 corresponds to 1, 2, 3, 4 delays. This x corresponds to 1 delay, this one, and that one corresponds to the input. Okay? In this example, we actually set the input to 0, right? The input was just 0. That's why I didn't have this XOR here. But usually people call it, in general terms, with the input, using this polynomial to represent this circuit. Okay? So why did I use a polynomial representation for this? Because in order to generate a unique sequences, okay, I'm saying 16 different possibilities, and maximum length sequence generator, bit sequence generator, you have to have a polynomial like this that cannot be factored. This cannot be factored. Factored meaning that you cannot write this as 2 polynomials multiplied with each other. Okay, that's the idea behind this maximum length bit sequence generator. This has got a name in algebra called primitive polynomial, because that cannot be factored into other polynomials. Okay? Of course, this is not the major topic of this class. I'm just giving you as a side information so you can keep it in mind. The reason that this generates this maximum number of possibilities is because the representation of this shift register corresponds to a polynomial that cannot be factored. Okay? Let me give you an example which can be factored. For example, the following polynomial can be factored. So let me just write it down. 1 plus x and 1 plus x cubed, for example. As you can see, I started from the factored version. Now I'm going to give you the multiplication using distribution law. You got 1 x cubed x, so there's x cubed, and there is x4, right? Now, you can see that this polynomial can be factored. Okay, because I started with the factored version. Now that I generated this polynomial. So let me draw the circuit that corresponds to this polynomial rather than this one, right? And there's only one difference between these two, right? There's an x cubed factor in here, x cubed. So which means I have to take this is my x cubed, right? I have to take this and then XOR it with the other. So maybe I can put an XOR here and then connect that to here, okay? Now this circuit here is represented by this polynomial, right? And this polynomial can be factored. That means there's a proof that this circuit is not going to generate maximum length bit sequences. Okay? If you don't believe me, and please don't believe me, go ahead and do this practice at home and you will verify it yourself. It's not going to go through all 16 possibilities. It's going to probably go through 12 or something. Okay, according to my calculations, it has to be something 12. Let me count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Yeah, 14 possibilities, sorry. Not 16, right? This is 16. You see? There are 16 possibilities here. This circuit has 14 possibilities. It's still close, but it is not maximum length bit sequence generator. Okay. So therefore, now you know the technique to check whether a given shift register with all these XORs, whether it's going to generate the maximum length bit sequences or not. Because now you know that there's a representation, a polynomial representation, then you look for if you can factor it or not. Okay? Of course, if this polynomial is very, very high degree, it's going to be really hard to see whether it's going to be factored or not, right? But I'm going to give you, of course, short polynomials, if that might potentially be a question in the exam or so. I may not ask such a question, but maybe in the future careers of yours, you may come across such a thing, and there's a simple checking mechanism to tell you whether this is going to generate a maximum length bit sequence. Okay? Any questions? I know these are kind of details that doesn't really pertain to the major body of the class, but I just wanted to give it to you because that might be handy, come handy later on. Okay, any questions? No? No questions? Question?
So if we say that this is the maximum, so that means getting all ones is impossible.
All ones?
I can't see any all ones here.
There is no all ones.
How come? That has to be all ones somewhere.
You just said 16, but there's only 15 here.
Oh, really?
Ah, there's
Maybe there's a mistake then. Because since this is maximum length bit sequence generator, that has to be all ones somewhere.
İşlem hatası.
Maybe, somewhere. So I didn't count it very well. 1, 2, 3,
Hocam sıfırdan başlayalım.
5, 6, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Then I'm counting one of those sequences twice then, right? Because there are only 16 possibilities for 4 bits. We can only count with 16, so there's one that is probably repeating itself. I don't see it. That's why I said, I kept saying, please check whether we encountered one of the previous sequences. Let's see. These are 3-bit sequences. I don't see any problem with the 3-bit sequences. 3-1 sequences. 3-1 sequence. This is a 3-1, 3-1, 3-1, 3-1. These are all good. How about 2-1s? That has to be 6 of them. So this is 2-1. 2-1, 2-1, 2-1, 2-1. One is missing, I guess. 2-1. So 2-1, 2-1, 2-1. It says 1-1-0-0 maybe, huh? Yeah, 1-1-0-0 is also missing, right?
No, it's 8.
1-1-0-0.
The 8th one.
Oh, this one, yeah, this one and that one. Okay, so actually, we don't have any problem with 2-1s, 3-1s, 2-1s, 1-1s. Let me just see if we got all 1-1s. So this is 1-1. This one, that one.
That's it.
Is that it?
No, the 6th one.
6-1, yes. So we got all 1-1s as well. So this is 4, 6, 4, and 1-0-0. Right? 1-0-0. So makes it 14, 15. Yeah, we need 16. That is 1-1-1-1. That is missing, I guess. And this is probably why, because we actually started with Q prime. That's probably why we don't have 1-1-1. That will never happen, because we started with Q prime. That's probably why.
We need to start from Q.
Yeah, I think it has to start from Q. But in that case, if you start from 0-0-0, I mean, you have to then initialize it. Otherwise, it will not count. Okay? So let me give a talk on this, because I'm not sure about the following. Would it be maximum length bit sequence generator if we need 15 or 16 possibilities? Sometimes people even don't, count all zeros to be one of those counting patterns. That's why people sometimes really exclude this and then say if it is 15, then we're okay. Because with 0-0-0, you cannot count. Whatever you do with the XORs, you will never count with all these zeros. That's why I started with Q prime. But if you, for example, forget about 0-0, start with this one and then connect the Q, then you will realize that all 15 possibilities will be counted. Okay? That's why probably. Okay? So I basically rephrase my definition of maximum likely sequence generator. Okay? So I exclude all zeros. Okay? Or in this case, I exclude all ones. Right? Because I started from Q prime. That's why I exclude all ones. That means the rest of the 15 possibilities must be counted by the counter in order for that to be called maximum length bit sequence generator. Okay? So I rephrase my definition. Okay?